Okay, this is a quick video about how to find the electric field from a continuous charge distribution, and in particular, I have in mind that we should look at, as an example, the electric field of a line charge. So in other words, the charge is smeared out over this whole thing. I can't point to where the individual charge is, and yet I still want you to tell me what the electric field is at point P. If instead I had given you the problem where I said, look, you got a couple of point charges, find the electric field at point P, you'd probably know what to do. You find the distance that each charge is away from that point, you find the electric field due to each of those charges, and then you add them up. It's pretty straightforward. What you're going to do with a line charge is actually the exact same thing. You're going to pick a piece of the line charge, and you're going to say that that piece of the line charge has a very tiny amount of charge, a tiny amount of charge, dq. And that dq is a distance r away from the point I'm interested in. Well, what electric field does that make? It makes a field that points away, and if I want to know what the magnitude is, I just use Coulomb's law, as I would for a point charge. In other words, I'm pretending this thing is a point charge. But of course, if I want to find the total electric field, I need to do it for all the point charges that are along the line. So the green one makes a line, and the blue one makes a line, and the gray one makes a line, and so on and so forth. Each one of these charges all the way along the line will make their own contribution to the field. And how do I find the net field at the end? I add them up. Except now, since I have an infinite number of infinitesimal pieces, I'm actually doing an integral. But it's a sum. I'm still adding up the individual pieces. Okay, so let's take a better look at this individual electric field from this individual charge. The charge is given by lambda dx. Why is that? Well, they tell us that the charge density is lambda, and lambda is charge per unit length. And so I can always say that a little bit of charge dq is the charge per unit length times a little bit of length. That's the idea there. By the way, if it wasn't uniform, if lambda was some weird thing, if lambda was like, I don't know, alpha a b to the x to the c, that's a ridiculous thing. But whatever, let's say it was, then fine, you still put it there. It doesn't make a difference in this case. It can be uniform or non-uniform. This technique will work either way. Okay, so we can write the electric field, so that's k dq, so I just plug in lambda dx, and then what's this guy on the bottom? Well, it's r squared, just Pythagorean theorem. So that's the hypotenuse of the triangle. Okay, there's a little extra wrinkle here though, and that is that the electric field is a vector, and that means that we need to find components, because if you add vectors, you must add the components of the vectors. You can't just add the magnitudes. But that's not a big deal. We know how to do that, right? The x component goes like cosine theta, and what's this angle? It's the same as this angle. So cosine is x over r. So there you are, x over r. One more piece. I'm not saying it's pretty, but it's pretty straightforward is what it is. And then dEy goes like sine theta. Okay, and then you say, okay, what do I do with those? You integrate them. You integrate them. That's it. You take these, you punch them into an integral, and notice you're integrating over dx in both cases. It doesn't matter whether you want the y component or the x component. You're integrating the charge, and the charge lies along the x direction, not the y direction. Okay? So I've just simplified these terms. My limits go from minus L over 2 to L over 2. Why? Because I decided to set my diagram up in such a way that I'm measuring x from the center. So this is the coordinate x equals 0. This is the coordinate x equals L over 2. And this over here is the coordinate x equals minus L over 2. So you have to think of these things as coordinates, right? Okay, so that's it. You do these integrals. So this integral, I didn't even do. I just punched it into integrator.com and it spat that out for me, okay? So at this point, you might say, okay, well, fine. You picked a really easy example. You cheated. You did the one where it's in the center. You don't want one in the center? Fine. I'll pick another point. Now it's not in the center anymore. What do? Well, I say that point is, let's say, x prime away from the center. So that would be given in the problem, say. And then how do you attack that? You do the exact same thing you just did. You just have a little bit of geometry to work out. So now, what's the distance from the charge to the point I'm interested in? Instead of being the old r, it's a new r. Look, so this whole thing is x prime. This is still x, and this difference is x prime minus x. And so you might wonder, well, how does that affect all the integrals? It's so easy. It's so easy. You just replace the x's with x minus x prime. This doesn't work anymore, of course. It's a new integral. So you'll get a different answer. This won't be the answer anymore. You'll get a new answer. But I just want to highlight how easy it is to get some different point, that there's nothing special about finding the midpoint. It's not a different technique. One other thing worth mentioning is, let's say that you don't want your integral to go from minus L over 2 to L over 2. You want it to go, I don't know, say 0 to L. Well, fine. Then set up your R from the end of the bar, and then you can do it that way. Why might you want to do it that way? I don't know. Maybe the person who gave you the problem said lambda equals ax squared, where x is measured from the left end. X is measured from the left end. And so in that case, it is easier, it's not necessary, but it's easier sometimes to set up everything going from there instead of from the midpoint. But it really is the exact same process. Okay, hopefully this was more helpful than confusing.